So let me start with this fourth lecture. So let me summarize what we did last time. So it was a bit of a heavy lecture with a lot of stuff, but not many detailed explanations. So, but I want to summarize all we did last time on one board. And what we will do today is basically use these tools that we have discussed in several examples and discuss several physical phenomena that we will want to understand in detail. Okay, so I hope after seeing these tools in action, what they are will be clearer. Okay, so what did we discuss? So we discussed the basic supersymmetric toolkit to go across strong coupling walls. Okay, so again, this is the picture. We have CFT1. We flow to CFT2 or tune some other parameters, not just RG scale, but some exactly marginal parameter. There is maybe some strong coupling regime, and then we want to understand, by studying CFT1, something about CFT2. And the number of tools that we have to do so is very limited. So tool number one is anomalies. Okay. Various 't Hooft anomalies. Okay. And this is not supersymmetric. This exists always. We don't need supersymmetry for that. Okay. And this is the basic, really the basic thing. I mentioned some type of anomalies, and again, I stress that this idea of symmetries, anomalies, and generalizations of these structures is a hot topic in recent research, and what we can do here, even for non-supersymmetric theories, is something which is developed as we speak. Okay, but basic ideas are the same. Then the second important thing is this hero of supersymmetry, the superconformal R symmetry. Okay. R symmetry in conformal field theories sits together in the same algebra with space-time symmetries, and because of that, because it is also a usual symmetry, it gives us a lot of technology to go across of these walls. So we discussed several things. So one thing we discussed is that this idea of A maximization, which under assumption of no emergent abelian symmetries, when we go across the wall, given symmetries of CFT1, gives us the superconformal R symmetry of CFT2. Okay, so this is a very simple algebraic computation that we can do on the data of CFT1, which gives us something non-trivial about CFT2. There is an important assumption, which we always have to remember, that once we go across this wall of strong coupling, no emergent abelian symmetries appear. If they appear, it doesn't mean that the argument is not correct, and we will see today a simple example where a U1 will emerge across the wall, but it will not matter, because we'll be able to really identify that U1 and see what that U1 does. But it might be that there is an emergent U1 that we will not know where it comes from and what it does, and then we're in problem. We don't know whether this A maximization works. Now, given this basic thing, this is really the basic idea behind everything, we can do many things. For example, one thing we discussed, that we can compute the conformal anomalies, A and C anomalies, and they are just given by combination of usual 't Hooft anomalies of this R symmetry. Okay, so this is something we can do. And then we can do a variety of other things. For example, we can compute various types of Witten indices. We have supersymmetry, and supersymmetry is a rich structure. We have a lot of supercharges in a conformal theory, so we can devise a lot of different supersymmetric indices, Witten indices, One index that we have discussed in detail was the superconformal index. Again, not too much in detail, but I just outlined the basic idea, is the superconformal index. This is the index which counts with weights local operators of our theories. We can consider other supersymmetric indices. There is by now a large variety of indices that we can compute. It's not infinite, but let's say order of 10, maybe less. Some depends how you count, but all of them behave. Witten will be offended. Okay, so there is some number of supersymmetric partition functions that we can compute. And very importantly for us, and we will see it today, by looking at these supersymmetric indexes, it's not just some partition function, some crazy function that we can compute, we can extract some physics from it. So I stressed that we can actually extract the symmetry of the theory across the wall, okay, modulo that marginal operators. So if we have marginal operators, what we will be able to see from the index is the conserved currents minus the marginal operators. So we will learn something about the symmetry, but not always everything. Okay? And again, today we will see a concrete example where we actually will see an emergent symmetry very cleanly from the index. That's not always the case because of these minus marginal operators. Another thing that you can do rather cleanly is to see all the relevant operators. Okay, so once you start from here, you have some operators, and you can wonder which of these operators are relevant once you cross the wall. And this is something you can cleanly deduce from the index, again, under the assumption that there are no emergent U1 symmetries. Okay, so this is some very interesting information, some very basic information you would want to know about the CFT that you can deduce by studying the starting point in a very particular way. Another thing that we discussed, okay, I'm getting to the end of this blackboard, so I need to finish with this list, is exactly marginal deformations. Okay. Exactly marginal deformations are a bit different from this logic, so we don't have a renormalization group flow. So these deformations are of the sort that you start from a CFT and you deform it, but without triggering a renormalization group flow. Okay, these are some parameters of this CFT. Okay, but again, this goes into the same type of logic because by tuning these exactly marginal couplings, you can start from some weakly coupled theory and start tuning them and go to strongly coupled regime. Okay, and once you do that, you can do all the other things that we discussed. Okay, you can understand what are the exactly marginal couplings, what are the parameters, and then you can just repeat the same type of logic that we have here. We can deduce various properties of this theory with the coupling when we go to strong coupling. A way to think about exactly marginal operators or couplings is that they take us between different CFTs. In a sense, in a very precise sense, when we have a relevant deformation, we turn it on, and in this language of looking just at the CFT endpoints, we kind of discretely jump to another CFT. Okay, we turn on a CFT, we start with a CFT, we turn on relevant deformation, the flow happens, and then we end up with another CFT. We kind of jump to another CFT. When we have exactly marginal deformation, we have a continuum of CFTs. We just continuously go between different CFTs. They are connected by a parameter. So in some sense, the case where we have parameters is kind of a continuum limit of this picture. Okay. So we can learn something about exactly marginal deformations. And the last point that I didn't stress enough, but it is very, very important, once we deduce something about the final CFT in this renormalization group flow, what we have to do, we have to perform all the possible consistency checks that we can. Okay, so consistency checks. What type of consistency checks we can have? Okay, for example, say we derive a conclusion that this CFT has some symmetry or There is some duality of the sort that we will discuss now. And what we can do, we can start deforming our starting point in different ways. For example, we think that something happens with one deformation and something else happens with another deformation. So we can start deforming with one deformation and with another and trying to connect the endpoints by themselves, just developing some kind of a network of understandings of how this space of CFTs, supersymmetric CFTs, behaves. Okay, that's it. These are the only tools, basically, that we have to study conformal field theory, supersymmetric conformal field theories, precisely, exactly. Of course, we can do a lot of things. We can start computing correlation functions and try to understand how they behave and so on. But these are hard questions. These things we can do exactly and precisely for basically any CFT that has NR symmetry. Any CFT, all CFTs have NR symmetry, but once we deform and preserve some kind of NR symmetry, we can play these games. All of these games are related to some sort of a counting problem. Okay? So all we can do, or the robust thing that we can do, is counting. So anomalies is counting, the indices is counting. Then we relate these A and C anomalies, which don't look like really counting something, but again, these are related to anomalies, so these are counting problems. Even when you will encounter some supersymmetric partition functions which depend on some continuous parameters, for example, if you have more supersymmetry in 4 dimensions, so if you go to 3 dimensions, you can compute other partition functions, which don't look like indices. For example, in 3 dimensions, you can compute a partition function on a round sphere. And it will depend on some continuous parameters. So it will look like you don't count anything. But always, you can trace these partition functions to some counting problems. For example, in the case of a round sphere in 3 dimensions, it's actually, the technology at least, can be traced to computing Winton indices in 4 dimensions. So it's you add a circle, you add an extra dimension, and then you are counting something. Once you take a limit to go to 3 dimensions, things don't look like a counting problem, and so on. But this is important to remember that basically all we can do exactly across these walls, and that's why the things work, is because we can devise some smart counting computations. Okay, so that's all we did last time. And now what we will do, we will try to apply this technology to some number of examples to understand how it works, and also to give examples of interesting physical phenomena. And then in the next lectures, we will try to understand these physical phenomena using tools coming from geometry in some sense. We will give these phenomena, at least some of them, a geometric interpretation. Okay, so that's what we are going to do. So let me start today by saying something more about this Witten index, something I didn't finish to do yesterday. So we defined this superconformal index as some partition function. Okay, so it was like that. So we have an index. We can compute for any theory. It depends on a variety of parameters, on P, Q, and some parameters which couple to charges of some global symmetry that we have in the problem. And I gave some trace formula for that. So trace -1 to the F, then P couples to some charges, Q couples to some charges, and this UI is coupled to some charges. Okay? The point why this Witten index is very useful is that if your CFT1 has a Lagrangian description in terms of fields, it is extremely easy to compute it. Okay? And that's what I'm going to tell you, how to compute these indices. Okay? Just practically, I will give you a prescription, and again, explain briefly where it comes from, and then we will use it to do various computations. So how do you compute this index? So you can consider the simplest theory possible. For example, a theory of a single chiral superfield. Okay? And let us assume that we assign this chiral superfield R charge, some general R charge R, and it is charged under some U1 symmetry with charge +1. So the R charge of phi, let us call it R, and some charge under the U1 global symmetry, which can rotate this field phi, let us just choose this charge to be +1. Okay, it's just a choice. We can make anything. Then the claim is that this index, the index of the single chiral field, has the following form. Okay, I will tell you what it is and then explain briefly where it comes from. So it's a very simple function. Okay, it's a product. It's a double product. Product of ij equals to 0 to infinity. 1 minus q I plus 1 p j plus 1 q p to the power okay, I get confused with my notations. Let me write it like that. Let me write it as a function, which I will define in a moment. I will call it an elliptic gamma function, and it has an argument, which will be q times p to the power r over 2 times u, where u is the fugacity for this U1 symmetry. And it has these two additional parameters, q and p. And just not to get confused with my notations, let me define it separately. Okay? So this elliptic gamma function is defined to be a double product, I and j equals 0 to infinity, 1 minus p I plus 1, q j plus 1, z minus 1 over 1 minus p to the power I, q to the power j, z. Okay? So you just take this monster, plug instead of z this guy, qp to the power r over 2, where r is the choice of r charge you have. And then you have u, which is the parameter, the fugacity for the U1 symmetry. You plug this thing inside the z in this function, and you get the index of a chiral superfield. Now, what did we say, what this index counts? This index counts local operators in your theory with some weight. So what are the fields, the basic fields that this superfield phi has? What is it built from? Okay. What are the basic ingredients in a chiral superfield? There is a scalar. There is some scalar. Let's denote it by phi, just a usual field phi, a scalar field. And there is a fermion, wild fermion. Let us denote it by psi of x. Okay, and there is an auxiliary field and so on. But these are the basic degrees of freedom that these guys have. So what are the operators that we can build? Local operators from these fields. Okay? These are some products of these basic fields. Okay? We can have this field to some power, this field to some power. Okay? This is a fermion, remember, so we need to be careful about that. And also we can have derivatives of these fields. So the generic local operator that we can build will be some product of these fields and various derivatives of these fields. Okay, so now we can understand with this understanding what is this index. Okay, in addition to the fact that the local operators are just products of these guys and their derivatives, this is an index. This doesn't count all the operators. It counts operators such that some charge that we have defined last time, and called H, which is combination of string dimensions, R symmetry, and rotations, this particular charge of the operator has to be 0. This is a Witten index. So we need to look on products of fields and their derivatives such that certain charge will be equal to 0. Okay? In a supersymmetric, when we have the supersymmetric algebra, the charges of all the states, like when we discuss the Witten index, and all of the operators when we discuss this index in this context, are non-negative by the same logic that we used when we discussed the supersymmetric quantum mechanics. Okay, so what we can do to compute this index is to just look on the basic objects that we can build from this field phi, which have H equals 0, and then multiply just them. If some basic object doesn't have H equal to 0, since all the H's are non-negative, we will not, once we introduce it, we will not be able to cancel it with anything else. So we need to find basic objects which contribute H equals 0 and then multiply these things. So what happens in this particular case with a very particular choice of supercharge, that what contributes to the index is the field phi. Okay, it's a complex field. Okay, so the charge depends on whether we look on phi or the complex conjugate of phi. So what actually contributes is phi and psi bar. Okay, and we have derivatives. How many derivatives we have in 4 dimensions? This is not a tricky question, just to wake you up. That's right. We have 4 derivatives in 4 dimensions, but only 2 of them have this h equal to 0. Okay, you can compute this quantum number h of a derivative, okay, and only 2 out of 4 derivatives have h equal to 0. That means that we can take these fields phi, psi bar, and 2 derivatives. So now we can fully understand this picture. Okay, so what do you think this double product is over? Derivatives, over the 2 derivatives. Okay, what is the numerator? The fermion. Okay, the numerator is the fermion. Okay, so we can either have some fermionic mode or not have it. Okay, so this is the not have it, this is have it. This is its weight. Okay, and then we can have derivatives of that fermion. And what we have in the denominator is the scalar field. Okay, so here these guys are phi's and derivatives of phi's, and these come from fermions and derivatives of fermions. Okay, that's it. That's how this index is computed. You need to do this analysis carefully to understand where all the particular numbers that appear here come from, but that's what happens. In particular, since I told you that phi, what contributes to the index is phi, and what contributes to the index is psi bar, one of them is weighed with u, okay, which is the fugacity for the u1. This is the bosonic part. But the other one is weighed with u to the power -1, because it is what contributes to the index is the complex conjugate and not the psi itself. Okay, and also there is this shift in the powers of p and q, and there is this thing that appears here, and that is because the R symmetry of the fermion and the boson is not the same. Okay, so once you take all of it into account, you obtain that the index of a chiral superfield is like that. Okay, it is a special function called the elliptic gamma function. It's some generalization of gamma function that you know. Maybe you know also a Q-deformed gamma function, so it's a kind of a doubly deformed gamma function. Okay, but the definition is extremely simple, and it is just comes out of this simple counting computation. Okay, this is one thing. So for free fields, we now understand. If we have free chiral fields, how to compute an index, we just take this definition and compute the index. If we have many chiral fields, we just multiply contributions of all of them. Okay, so we can build operators from products of fields in each one of the chiral superfields, so we just compute a product. Okay, so now another piece of information is, say we have a gauge symmetry. Okay, so we need to introduce also the vector superfields, and we need to project on gauge invariant states. Okay, so the way to compute the index of a gauge theory is very simple. So there will be something like that. There will be contribution that I will denote by QQ, PP to the power rank of G. There will be 1 over the dimension of the Weil group, which I will denote like that. And then there will be some kind of a contour integral over the Cartan generators of the group. So it will be pi from I to the rank of G of d zi over 2 pi I zi. Then we will have 1 over gamma, the same elliptic gamma function that we defined here, over the roots, and I will now say precisely what this means, QP, the same gamma function with some argument that I will define, times the contribution of all the matter. Okay, so that's what we will have in a supersymmetric theory. We will have matter fields, we will have vector fields, and vector fields together with projection on gauge invariant states will produce this type of an integral with this thing. So by these gamma roots, I mean the following thing. So let me explain this by giving you an example. If the gauge group is SUN, then what appears there, this gamma E roots, is nothing more or less than the following thing. We just have a product over all combinations like that. Okay, product of I not equal to j. Okay, where I and j run from 1 to n minus 1. Okay, this is for SUN, and you can do it for other groups. For example, for USP to n, we will have similar thing, but now there will be gamma zi to the power plus or minus 1, zj over to the power plus minus 1, qp, and also gamma e z plus minus 2, zi plus minus 2, qp. Okay? If you remember your group theory, this corresponds to roots of the corresponding groups. Like here, the roots are ei minus ej, and here they are plus minus ei plus minus ej, and plus minus 2 of ei. Okay? When I write arguments of gamma functions in this form, like I have plus minus 1 in various places, what I will mean is that I will need to take all the choices and multiply them. Okay, so what this means is that I take gamma e of zi times the j, multiply it by gamma e of zi to minus 1 zj, multiply it by gamma e of zi zj minus 1, and so on. Okay, so these choices are just a compact notation to multiply everything. And finally, I need to tell you what these guys are. These are Q-Poch-Hammer symbols. So the definition is that some number z q, this bracket, is just product I equals 0 to infinity of 1 minus z q to the I. Okay, this is just a definition. And again, this expression comes from the same type of counting problem, but now we count the fields of a vector multiplet, not of a chiral multiplet. Okay? So in the end of the day, the technology is extremely simple. You want to compute the index of a gauge theory, you just take your chiral fields, you compute the index for each one of them, and then you compute such an integral. Okay, so index in general is some contour integral over a product of elliptic gamma functions. Okay. So with these definitions, let us now discuss several examples. Yes? W is the order of the Weil group. So for SUN, it will be n factorial. And then for every group that you want, you need to figure out what that is. It's some numerical factor, some simple numerical factor. More questions? Yes? Yes, it doesn't have to be free field. That's a very good point. So it is a chiral field. Okay, the computation of the index it doesn't matter whether it is a part of interacting theory or it's really a free field. The place where the place where the information whether it's free or not will enter is in the value of this R symmetry. Okay, so if it's free, the superconformal R symmetry is 2/3. Okay, and then if it's not free, for example, if we turn on some kind of superpotential, it will fix R symmetry to be something else, so it might change the R symmetry and so on. But the computation is exactly the same. Yes, so that's a good point. When you compute this thing, I already took into account the equations of motion, okay? And it works. Basically, the way to think about this index, you really compute it for a free theory, and then you start flowing. But it is important that you introduce only symmetries which are preserved by the deformation, and that's why you have a choice of an R charge. Okay. I will do now an example. Okay, so now let us do a very, very simple example. Let me take two fields. Let me call them phi1 and phi2. Two chiral fields, no gauge interactions. Okay, and I turn on a superpotential, which has the following form. It is M phi1 phi2. It's quadratic superpotential. What does this mean? What kind of a theory we have? If we have a quadratic superpotential, Okay? This is the hint. Okay? This is a massive theory. Okay? You write a potential for this theory, you derive the potential for this theory, and you find that you have just two massive fields. Okay? So what happens in this picture of going across the wall? So we start with a theory with two chiral superfields. We turn on a mass term, we flow, and what we will get in the infrared? Like in deep infrared, we go much below the scale set by the mass. We go to the fixed point. What we will get? Gap theory. We'll get nothing, okay? Not exactly nothing. We will get just the vacuum. We will not get excitations over that vacuum, so we'll get just nothing, just the vacuum. What is the index of nothing? The answer is not 0. 1. Okay, where this 1 comes from? The vacuum. Okay, so if you count states, that's the vacuum, with the supersymmetric vacuum you are left with. If you wish to count operator, this is the identity operator. That's what it contributes, and you don't have any other operators. So the index of this theory is expected to be 1. Okay? Because I claim that the index is invariant undergoing across this wall, I know what this will happen with this simple theory across the wall. It's a massive theory, so it has to be gapped. The index has to be 1. On the other hand, I told you that there is this complicated technology to compute this index. So it better work that when we apply this technology to this simple case, we will get 1. Okay, so let us perform this computation. For that, let us assign some charges to the various fields. So we have two fields, and we know that the R charge of the superpotential has to be equal to 2, okay? So let me assign an R charge to one of the fields, the R charge of phi 1, let me call it R. Then the R charge of the second field is fixed. What will be the R charge of the second field? 2 minus R, okay? And also, we have a U1 symmetry. We can rotate phi 1 one way, and phi 2 we can rotate the other way. Okay? So we can assign Q of phi 1, say, to be plus 1, and then Q of phi 2 to be minus 1. Okay? That's it. Using this information and the technology appearing on the blackboard, we can compute the index, and we expect that index to be equal to 1. Okay? So let us compute it. So what is the index? So we're asking whether the index is equal to 1. We have two chiral superfields, so we just have product of two of these elliptic gamma functions. So we just write them explicitly. So we have gamma E. The field phi 1 contributes QP to the power R over 2 times U, where U is the fugacity or parameter for this U1, okay, QP, times gamma E, and then something else. The charge under U1 is minus 1. Okay? Then we have QP. And also the R charge is not the same. Okay? It is 2 minus R. So we'll have QP 2 minus R over 2. Okay? So we have two complicated functions multiplying each other. But now let us see what is actually happening. Let me write these elliptic gamma functions using these definitions. So what you will get is the following. Each one of them is a double product of I and j equals 0 to infinity. And then we have 1 minus QP 2 minus R over 2 U minus 1 QI Pj over 1 minus QP to the power, there is a small r here, R over 2 U QI Pj. Okay, this is a contribution of the first field. And then there is a contribution of the second field. What will be the contribution of the second field? Instead of R, I need to put 2 minus R. So what I will get? Okay, what I will get here? 1 minus QP to the power R over 2. The U1 charge of the field phi 2 is opposite. Okay? So what I will get here is U. Okay? 1 minus QP 2 minus R over 2, U minus 1 QI Pj. What is this? This product is equal to? 1. Okay, how is it equal to 1? The scalars of one field kill the fermions of the other, and the other way around. So in the end of the day, I just get a product of ones, and we get indeed that the index of a massive field is equal to 1. Okay? So this is a simple example of how you go across these walls. Here you know the physics, nothing is mysterious. Okay? You just have a gap theory, and this computation of the Witten index is consistent with that. Okay, and if you wish, the fact that it works, it's a simple property of these elliptic gamma functions. Okay? They had to satisfy it because they are an index. Okay, is this clear? Yes. Well, it is a superconformal index, but the theory is gapped. So, you know, the conformal symmetry, it's a topological theory, which is trivial. It has only a vacuum and nothing else. Okay, so in that sense, like, the question of what is superconformal R symmetry is mute. The R symmetry is acts on nothing. Okay, so it's a really, really trivial example. But it had to work, and you see it works in some way which is not completely trivial. Okay, so with this example, let me discuss more interesting examples of physical phenomena. Okay, so let me introduce you to a phenomenon known as infrared duality or Seiberg duality, and let us discuss what it is and how we know it is correct. Okay, so again, I will keep this picture on the blackboard. Okay, so example of interesting dynamics. So here there was a trivial, non-interesting dynamics of a massive field where we got a gap theory. Now let us discuss a more interesting example where we start with a gauge theory as CFT1. So we start with NSUN, SQCD. Okay, so we have an SUN gauge group, and we have matter fields. We have NF chiral superfields that we will denote by Q, which are in fundamental representation of SUN, and NF chiral superfields that I will denote by Q tilde, which are in the anti-fundamental representation of the gauge group SUN. And we want to understand what this theory does when we go across this wall. In general, this theory will flow. We will soon ask ourselves, what is this gauge coupling? So the only interaction we turn on is the gauge coupling, and we will ask whether the gauge coupling is relevant, marginal, or irrelevant. But assume for a moment it is relevant, that these are asymptotically free theories. We flow somewhere, and we want to understand what is this CFT2. Okay, so here the question is much more interesting than before. So this is our starting point. And now let us discuss this claim of Seiberg. And we will mention it, and then we will discuss it, what it means. So the claim is as following. If you choose this NF parameter to be in certain range, so if we choose NF to be smaller than 3n, but larger than 3/2 of n, okay, the n is the n entering this SUN gauge group. It's sometimes called the number of colors. Okay? This is the number of colors, and this is the number of flavors. If we are in this region of parameters, if we choose an F in this window, which is called the conformal window, then the claim is whatever this theory flows to is the same thing to which the theory with the gauge group SUNF minus n will flow to. Okay, so you consider a different SQCD with a different gauge group, SUNF minus n, SQCD, with other fields, with NF fields, which will denote by small q in a fundamental representation, and NF fields, which will denote by small q, which are in anti-fundamental representation. But we also have additional fields, which I will call Mij, and we have an F squared fields like that. So, and the point is that these fields now couple through a superpotential to these fundamental fields Q and Q tildes, and they couple in the following way. We have M coupling Mij, Qi, Q tilde J. So this theory has only gauge interactions, but here we have gauge interaction with a different gauge group, and we have a matter which looks similar, but we also have fields which don't transform under gauge symmetry, but they do couple to some gauge invariant combination of the quark fields. Okay, so this is a statement. Okay, we will discuss it in a moment. Another statement or related statement is like that. Okay, if we go outside of this region of parameters, okay, in the following way. Okay. If we are now not in the region which is written there, but say we are in the region where NF is bigger or equal than NF plus 1 and smaller or equal than 3/2 n, we look on SQCD in this limit. What we will soon discuss that in this region of parameters, both of these theories are asymptotically free. Okay, they both flow to some strong coupling. If we're in this region, this theory is still asymptotically free, but this theory is infrared free. Okay, so the statement is then that, let me draw a picture. Let me draw a picture here. So here we have this CFT1, which is just a free theory of this type. Then we turn on these gauge interactions. We flow to CFT2, which is some CFT that we don't know what it is. It's some strongly coupled CFT. And then we call this theory CFT1 prime. CFT1 prime. And what this statement of Seiberg duality tells us is that this CFT prime flows to the same CFT2. Okay? So it doesn't, this duality argument doesn't tell us what this CFT is, but it tells us something else which is non-trivial, is that there are two CFTs which flow to exactly the same CFT in the infrared. Okay? Notice that the number of colors, the number of gluons in the two theories is different. The interactions are a bit different. But the claim is that in the infrared we get exactly the same theory. So it's a very, very surprising statement. Okay? Now, this is the statement in this region of parameters. In this region of parameters, again, one theory, the CFT1 theory, is asymptotically free. Okay? So we start with CFT1, and we flow. Okay? And then we get this something we call CFT2, or let me call it QFT2. Okay? And what this duality tells us in this region of parameters, so we start from a theory, we deform it with a relevant operator, something funny happens in the middle, and then in the end we get this theory, which is CFT1, QFT1 prime, but with this region of parameters, this QFT1 prime is not asymptotically free, it is infrared free. So it flows to a free theory. So the description here is as a free gauge theory. Okay, we start with an interacting gauge theory with some gauge group. There is strong coupling dynamics happening, and then in the end, we go outside of this wall, and we end up with a weakly coupled gauge theory, but this gauge theory has completely different degrees of freedom. Instead of this SUN gauge theory, it is SUNF minus N gauge theory. Okay, is this clear? This is more in vein of what we were discussing, but these phenomena are related to each other. Okay, so let me just very briefly tell you, okay, or use the technology that we use to kind of indicate how we know which theory is asymptotically free, which theory is infrared free. Okay, so what do we need to do to discover whether a theory is asymptotically free or infrared free? We need to understand whether the gauge coupling is relevant or irrelevant. Okay? And one technology we learned to do so is to compute an anomaly, which is traced RG squared. Okay? I remind you that we discussed that if this number that we will compute turns out to be positive, the gauging is relevant. If this number turns out to be negative, the gauging is irrelevant, okay? Infrared free, or in the first case, asymptotically free. Okay, so let me compute this number for this gauge theory. Okay, so we have various fermions in this theory. So there are the gluons. We performed this computation already in the last lecture for a special case when NF equals 3n. I remind you, and we found that this thing was actually 0. Okay, now I perform the same computation, but with the general NF. So there is the contribution from gluons, which come from the vector multiplet, and it just gives us n, okay? Again, trace of g squared for a joint representation is n, and R symmetry of the gluons is 1. Okay, so we get this n, and then we have the contribution of the matter fields. So we have the half coming from trace g squared for the fundamental or anti-fundamental representation. Then we start from a free theory. So in a free theory, the R symmetry of all the fields is equal to 2/3, and we need to subtract 1 from it to get the R charge of the fermions. And then we multiply by twice NF. We have NF fundamentals and NF anti-fundamentals. Okay? So what this is equal to, it's equal to n minus NF over 3. Okay? And now we see, as we found in a previous lecture, when NF equals to 3n, this number vanishes. When NF is smaller than 3n, so when we are inside this domain, then the theories are asymptotically free. Okay? You can do the same computation for the dual theory, and you will find that if you cut this NF from the other side, then also this theory is asymptotically free. You see, we go from this to that theory by, this has an n and this has an f minus n. So it will give you us another bound. Okay? So just do this computation and find that when you are in this region, both theories are asymptotically free. If you are outside of this region, if you are here, then one of them is asymptotically free. The original theory still has an f smaller than 3. It has even an f much smaller than 3n. So it's still asymptotically free, but the other theory is infrared free. Okay, so the computation to decide what is the coupling, how it behaves, is this very simple technology that we have discussed. Okay? Okay. So this is a claim. Before discussing this claim, let me draw a picture. Okay? There is a way to encode this duality in a picture called the quiver diagram, which is very useful. It saves a lot of space and time. So let me draw a picture for these two theories. For these two theories that we discussed. So a way to graphically denote a theory, an SUN gauge theory with fundamental matter, is as following. For each gauge group, we draw a circle. So for SUN, we draw a circle, and we put the n inside. It just means that we have an SUN gauge theory. Then, say, fundamental matter will be denoted by arrows which go outside of the circle. We have NF such things. So NF is not a gauge symmetry. We will have an SUNF global symmetry. So there will be a double arrow. There will be an arrow going from SUN gauge symmetry to SUNF global symmetry that we will denote like that. And then we have the anti-fundamental matter, which will be just the arrow going the other way, going from the flavor into the gauge. Okay, so it's a graphical representation of the SUN SQCD with the NF flavors of fundamentals and the NF flavors of anti-fundamentals. Okay. Then the dual theory is, we can draw in exactly the same way, but the numbers are slightly different. So we still have fundamentals and anti-fundamentals. We still had the same number of flavor symmetries, but the gauge group was different. The gauge group was SUNF minus n. Okay? And in addition, we had these fields that I called Mij. Okay? They are not charged under the gauge symmetry, but they are charged under both of these global symmetries. Okay? Remember that we had a superpotential, which looked like Mij, Qi, Qj, tilde. Okay? So this I is SUNF index, this J is SUNF index, different SUNF indices. So these fields are in bifundamentals of the two SUNFs. So I write them as an arrow between these two guys. Okay? So this claim of Seiberg duality is that this theory is equal to that theory in graphical language. And again, what equal means is different depending on where you are in the range of parameters. If you are in this conformal window, it means that both of these theories are asymptotically free and they flow to the same CFT. If you are outside, one of these theories is asymptotically free, another is infrared free, and a way to think about this statement is that one theory describes the other theory in the infrared. Okay, so now the important question. This is a conjecture, this is a claim of Seiberg that this statement is true. How do we know that this statement is true? Okay, so what do you think? The answer is on the first blackboard that I wiped out already. We just have to check what we can check. So the first thing that we wrote on that first blackboard is anomalies. Okay? So what are the symmetries that these theories have? Okay? So these theories have an R symmetry. Okay? We have an R symmetry. We have two SUNF symmetries. Okay? We have an SUNF rotating the fundamentals and the anti-fundamentals. We have another symmetry, which is a baryonic symmetry. You can check that it is not anomalous. We can assign charges, say, +1 to all the fundamentals and -1 to all the anti-fundamentals. This is a non-anomalous symmetry. And so these are the symmetries that we have. The dual theory has the same symmetries. Okay, it has SUNF, SUNF, and it has an R symmetry. The R symmetry assignment here and here is not the same. Okay, you can work out what will be the non-anomalous R symmetry in both cases. And also there is some map of baryonic symmetry. Also here there is a baryonic symmetry, but you should identify the symmetries in some way, and I leave it as an exercise. So what you can do, you have these symmetries, and now compute anomalies for all of these symmetries. Compute trace R cubed, trace R, trace R U1, trace R squared, U1 baryon, trace R U1 baryon squared. Compute all of these anomalies on one side and on the other side. If one of these anomalies doesn't match, this is garbage. Okay? So there are many anomalies to check, and all of them work. Okay? By work, I mean you compute them here, and you compute them here, and you get exactly the same numbers. Okay? That's one thing you can do. Another thing you can do, and this is basically the content of original paper of Seiberg, it's checking these anomalies. And then another thing you can do, you can try to map operators. There are some operators which satisfy special properties. Basically, you can trace them across of this wall. Back in the 95, that's what people could do. So you could trace these operators and see that they are the same, and then do various consistency checks. For example, you have this statement of duality with some number of flavors. Now you can give, you can turn on some mass terms, for example, on one side. For example, you have here operate fields Q and Q tilde. You can turn on, in addition, a mass term of the form Qi tilde, where you don't sum over i's. So you will get smaller number of flavors here. And then the dual theory should be different. So you can trace what is the formation is on the other side. This will correspond to turning some vacuum expectation values. This is some field theoretic computation you can perform. And you see that by starting with such a duality, you get another duality, but which is the same. So there is some consistent picture of dualities that you can find. Okay. Now, nowadays, anomalies are still a thing that we will check. But these operators, tracing of operators, is basically all of it encoded in computing these indices. What indices do for you is, without thinking, they actually focus on these operators that you can trace across the strong coupling wall. Okay? So one thing that you can do, which is very simple, is compute indices, these various types of Witten indices, in particular the superconformal index, and ask yourself, is the superconformal index of this theory equal to that theory? Okay. We perform this computation explicitly for the simple case of a massive field, and we found that we get what we expect, so we can perform it here. Okay? So let me write one example of such a computation. Oh, I'm slow with time. Okay, so let me write an explicit computation only for one case. Let me take n to be equal to 2. Okay, a special case of this type of duality. We have an SU2 gauge group, and I take an f equals to 3. Okay. In this case, I'm not in this conformal window. I'm in this other regime. Okay, and so this theory is asymptotically free, and there will be a dual theory which is infrared free. Okay, what will be the infrared theory? What will be the gauge group of the infrared theory? So it is SUNF minus n. So it is SU1. What is SU1? It's no gauge group. Okay? So the statement is that here we have SU2 with 3 flavors, and the dual side is not a theory of, it doesn't have gauge symmetry. It only has gauge singlet fields. Basically, these Q's become gauge singlets, and these M's are gauge singlets. So we have just a collection of free fields with a superpotential. Okay, how many fields do we have? So we have 3 fundamentals of SU1, which is just 3 fields. 3 anti-fundamentals of SU1, again, just 3 fields. So these are 3 gauge singlet fields. These are 3 gauge singlet fields. And these are 9 gauge singlet fields. So in total, the dual theory is just 15 free fields, of 15 chiral fields with some cubic interactions. Okay? So now let us write down at least one index of a gauge theory in full glory and see what the statement is. So the statement is like that. You compute the index of the gauge theory first. It is an index of SU2 gauge theory. You follow our general definition. So this theory is rank 1. So we'll have Q, P, P. Then the rank of the order of the Weil group is 2. It's an SU2 theory, so we'll have a half here. Then we have integral over du over 2 pi iu. Okay, we have, again, a rank 1 theory, so it's just a single integral. And then we have a contribution of all of the matter fields. So we have 3 fundamentals and 3 anti-fundamentals. So, and what we'll have is product of I equals 1 to 6, gamma E of QP to the power 1/6, U to the power plus or minus 1, and then AI, QP, okay? Now, this is an SU2 gauge theory. For SU2 gauge theory, there is no difference between fundamentals and anti-fundamentals. This is the same representation. So instead of saying that I have 3 fundamentals and 3 anti-fundamentals, it's the same as saying that I have 6 fundamentals in this case. So I have 6 fields. This U plus or minus 1 is how you would weigh fundamental fields. Okay, this is, if you wish, the character of a fundamental is U plus U to the power minus 1. Okay, and this is what appears here. These are the charges of the components of the fundamental representation under the Cartan U1 symmetry. That's another way to think about it. Then we have these parameters AI. What do you think these AI are? Okay, we have an SU, an F times SU and F times U1 baryon global symmetry. For SU2, because there is no difference between fundamentals and anti-fundamentals, we actually have an SU2NF global symmetry. So we have an SU6 global symmetry. So these AIs are just parameters corresponding to this SU6 global symmetry. So there is a condition that this product of AI, I equals 1 to 6, is equal to 1. So again, these are parameters labeling SU6. Okay? So this is the contribution of which type of fields to the index? Of the matter fields, okay, of the chiral fields. And then we need also to introduce the contribution of the gauge fields. Again, this is just SU2, and it will be given by gamma of E, U to the power plus minus 2, QP. Okay? So this is the computation of the index of this gauge theory. Very explicit. And I really suggest you to take Mathematica or other tool that you use and start computing this thing as a series, say, in this parameter Q and P. Assume that Q and P is some numbers that are smaller than 1, and expand this integral and compute it as a power series in Q and P. On the other hand, this has to be equal to the contribution of 15 chiral fields. Okay? If you trace the charges and symmetries correctly between these two theories, the contribution on the other side you can write as following. You have product of I smaller than j, gamma E of QP to the power 1/3, AI, AJ of QP. Okay, so you have I smaller than j. So you have 6 times 5 divided by 2, which is 15 gamma functions, which correspond to the 15 fields that you have here. So if this duality is correct, this equality has to hold. Okay, now, unlike what we did before with the massive field, where we could immediately prove the identity which followed from physics, this is hard to prove. I will not encourage you to prove it because I don't know how to prove it. Okay? But it was proven by mathematicians. Okay? This identity was proven by mathematicians before they knew, like after Seiberg came up with the Seiberg duality, but before physicists knew that this is something they want to compute. So this is kind of a weird situation. Okay? After the physical statement was made, but before the index computation was discovered. Seiberg duality is roughly 94, 95. Definition of the index, as I defined it, is about 2005 by Rommelsberger and Maldacena, Kini, Minwala, and Raju. And the proof of this identity is like 2000, mathematical proof of this identity. Okay, so this identity was proven, and I really encourage you not to prove it, but to check it on Mathematica. It's really miraculous how this thing happens. And you can write these types of identities for any of the Seiberg dualities, and basically all of these identities for Seiberg dualities that I defined here were proven by mathematicians. Again, before they knew what they were doing. They just proven some identities. Yes?
Why would mathematicians look at that?
Excellent question. I don't know. I still don't know. Okay? Well, there are various ways. So it's not, I don't really know, but you know, these elliptic gamma functions are special gamma functions, so they generalize a lot of special functions that you know, for example, the usual gamma function. For example, this integral in some degeneration limit, where you send some of the parameters to some limits, is the beta integral that you have in string theory. Okay, this is a generalization of the beta integral. That's how the first person who computed it, his name is Spiridonov, who proven it, and he viewed it as a generalization of a beta integral to this level, to the elliptic level. And you know, they came up with, there are people who study these special functions for a variety of reasons. There are a lot of reasons to study special functions, ranging from number theory to physics. So all the mathematicians have their own motivations. I don't know how you get up in the morning and you start proving these identities. I don't know. Okay, but for example, just to mention another thing, from physics there are many identities which are like that which appear. We know they have to be correct because of physics. We are not sure. All the statements, it's very important to stress it. There is no proof of Seiberg duality. It's a conjecture. Okay. Even now, it is still a conjecture. We have checked it in a variety of ways, but it is still a conjecture. All we say in physics is a conjecture. But from such conjectures, another thing important to stress, mathematical equations follow. Okay, this is an equal sign. This is not, we think it's something like that. This is an equal sign. If you compute it and it is not equal, this is garbage, okay? So we produce this type of identities, and we have a lot of dualities that we can come up with. There are a lot of identities. Mathematicians don't care about them, okay? They have their motivations to proving these identities. If you come to a mathematician, look, I think this is correct, he will say, okay, but why should I care? You know, in the same sense that I say, I don't know why mathematicians are interested in that. it's a bit, when you talk to these mathematicians, it's a bit, they are amused that somebody, comes up with the same equations and they have no idea why. So it goes both ways. Okay. So this is a basic example of a duality and how you check it. Yes?
For the dual theory in the IR, the gauge diagonal is free, but we still have the interaction from the W potential, right?
Yes, there is a collection of 15 fields with this superpotential. So it is naively, these are not free fields. There is an interaction. What this interaction does, it couples like the charges of various fields. Like it's not the symmetry group of this theory is not U15. Okay, the superpotential breaks it. But as we discussed last time, this theory is free. This is just a collection of free fields, and it follows to a free theory. Okay, because it's a cubic interaction. Naively, it's marginal, but we have proven that all such things are marginally irrelevant. So in deep IR, it is a free theory. So in that sense, this is an excellent point. So you start from this theory, you have an SU6 global symmetry. But once you hit infrared fixed point, this SU6 symmetry is actually enhanced to U15. Okay? It's not visible in this description. This description is not the description of the fixed point, is actually a description slightly away from it. So it actually describes the physics near the fixed point, but we can easily understand what this fixed point is because this is irrelevant. These are just 15 free fields. Okay? Okay, so again, you can play this game for any Seiberg duality that you want, and you can do a variety of other checks. You can compute other partition functions. You can study various other protected these counting problems that I mentioned. Until now, everything works. All the computations work. So now let me discuss another interesting case of duality, okay, or rather of emergence of symmetry. Okay. So let me study a theory, which is in this graphical language, it looks like that. It's SU2 with 8 fundamentals. Okay? In the language of splitting these fundamentals to fundamentals and anti-fundamentals, we have 4 fundamentals and 4 anti-fundamentals. So in that language, NF equals 4, because NF counts the number of fundamentals or the number of anti-fundamentals. If you look on the Seiberg duality, which is written here, what will be the dual theory? What will be the gauge group of the dual theory? It will be again SU2. So it will be again an SU2 theory with 8 fundamentals. Okay? But you will have these gauge singlet fields. So it's not, you don't go exactly to the theory you started with. You go to something which looks like the same gauge theory, but with an additional superpotential and additional fields. So Seiberg duality in this particular case is non-trivial, but it's some kind of self-duality. It's like you start from a theory or with the same type of a theory with additional interactions, and then you end up with the same CFT. Okay? We will discuss that in the end. But let me just consider this theory by itself, and I will do something weird to this theory, and we will discover something interesting about it. Okay? So what we will do is the following. So I look at this theory, and instead of thinking of it as a theory of 8 fundamentals, I will think of it as a theory of 6 fundamentals and say 2 anti-fundamentals. Okay, I can do that. Okay, I did nothing. I just split the 8 into 2 and 6. Okay, this is the same theory as I had before. But now I introduce gauge singlet fields, which are in the antisymmetric representation of this 2-index antisymmetric representation of this SU6. So let me call these 6 fields Q, and these 2 fields Q tilde. This is not the same Q and Q tilde I had before. I call this 6 a Q, and these 2 fields I call a Q tilde. Okay. And what I do, I introduce 15 fields that I will denote by this capital M. These are additional fields that I introduce, and I couple them to Q, Q. Okay, I build a gauge invariant out of QQ. To build a gauge invariant out of fundamental, I need to anti-symmetrize the gauge indices. So I will anti-symmetrize also these indices. So I will have 15 fields. So I turn on such a superpotential. Okay, so this is the theory I will construct. And graphically, what I will do, I need to represent somehow these 15 fields that I will added. So I will denote them by this X that I will draw on this diagram. Okay, so what this X means, it denotes these fields M, and the fact that they couple to this Q squared through this interaction. Okay, so now what we want to do is to analyze this theory. Okay, this theory is extremely simple, but it will lead to a surprising result. Okay, so first of all, what is the global symmetry of this theory? Okay, let us start with this theory. What is the global symmetry of this theory? It's SU8, and we have the U1R symmetry. Here, we've broken this SU8 to SU6 times SU2, and there is a U1. There is a U1. We can assign a U1 charge to this and U1 charge to these fields in a correlated way, so it will be anomaly free. I will soon write this assignment. And of course, we also have a U1R symmetry still. Okay? So naively, this theory has an SU2 times SU6 times U1 global symmetry, in addition to the R symmetry. Okay? What we will see, we will basically prove it under assumption of no accidental U1 symmetries, that in the infrared, the symmetry group of this theory is E6 times U1. I don't know how much you know of your group theory, but it is one of these exceptional groups, E6, E7, E8. It is a rank 6 group, and it has a maximal subgroup, which is SU6 times SU2. So what you see in the UV Lagrangian is only the SU2 times SU6, but this theory in the infrared has actually an E6 global symmetry. Okay, so how would you do that? So there are various things that one needs to do. So I will not do all of them on the blackboard, but let's just go through them. So first thing, we need to show that this theory is asymptotically free. Basically, we have shown that already. Go to the parameters, and you will see that the gauge coupling is such that it is asymptotically free. This theory flows to some SCFT. Once you flow to the SCFT, you need to discover what is the superconformal R symmetry. How do you do that? You do a maximization. Do a maximization, and you will find that the superconformal R symmetry, basically the R symmetry, it will be also the natural R symmetry you will find here, assigns for all of these fields, let's call these fields Q in this theory, the superconformal R symmetry will be a half. Okay, this is just a computation of a maximization. Okay. Basically, there is no A maximization to perform here. Why there is no A maximization to perform here? When you do A maximization, R symmetry and abelian global symmetry, but there are no abelian global symmetries here. So the superconformal R symmetry that you will get here is basically the only non-anomalous R symmetry that you can find. Okay? So this is the R symmetry in the infrared. Now we want to turn on such interaction. How we discover whether this interaction is relevant, irrelevant, or marginal? Okay, we flow to the infrared of this theory, and then we make this deformation. Okay, so what we need to do, we need to compute the R charge of this deformation. What is the R charge of this deformation at the fixed point of this theory? These fields have R charge a half, each one. So the R charge, the contribution to the R symmetry of these guys is 1. This is a free field before we turn an interaction. So the contribution of this to R symmetry is 2/3. So the total the R symmetry of this superpotential is bigger than 2, smaller than 2, or equal to 2. What is the correct answer? Smaller than 2. It's 1 plus 2/3 is smaller than 2. If it's smaller than 2, it's relevant. Okay? So this deformation that we turn on is relevant. So the way to think about what I'm telling you is, as I mentioned before, always think of turning on one deformation at a time. First, you turn on gauge coupling. You flow to a CFT. Then, at that CFT, you turn on this superpotential, and you again flow. Okay. At this point, at the starting point, is this superpotential relevant, marginal, or irrelevant? If I would turn on it first before turning on the gauge interactions. Okay. What are the R charges of these fields when I start the theory here, before turning on gauge interactions? All of them are free, right? Okay, so this will be marginal. Okay, so if I turn it on first, before I turn on the gauge interaction, this is marginal, and if I don't turn on this gauge interaction, is marginally irrelevant, so it will not do anything. So it's important to do things in certain order, and that is the order in which I do things. Okay, so you discover that you flow to some CFT, and now let me write charge assignments under various symmetries, under this SU2, SU6, and U1 symmetries for various fields. To do something else, in addition, I will also introduce another superpotential term, which will simplify my life, but I don't need to do it. I will introduce a single field, gauge singlet field, which I will denote by small m, and it will couple to this Q tilde, Q tilde. Okay, again, all the indices anti-symmetrized. Check that it also is a relevant operator. The argument is exactly the same. Okay. So now let us try to understand what this theory is in the infrared. So for that, I first tell you what are the charges. So we have various fields. We have Q, Q tilde. We have this M and small m that I introduced. And we have the various symmetries. So we have the SU2 gauge symmetry. We have SU2 global symmetry. And we have SU6 global symmetry. We will have a U1, additional U1 global symmetry that I will denote by U1H. And we have a U1R symmetry. Okay? And first thing we need to do is to understand what are the charges of various fields which appear here. Okay? It's a simple argument to perform. So both Q and Q tilde are in the doublet of the gauge SU2, and the fields M and M, the capital M and small m are singlets of the SU2. Okay? That's how I define them. Then what are these fields, how they are transforming under the global symmetries? Again, the fields Q doesn't transform under this SU2, they are transformed under this SU6 and vice versa. So the Q is singlet under this SU2, this is a doublet under this SU2, and this field is singlet under everything. This field is in a 6-dimensional representation of this. It's a singlet of this. The field M, as I mentioned, transforms in a 15-dimensional representation of SU6. So what is this representation? So we have we have two Qs. We anti-symmetrize the indices, so we get a 15-dimensional representation. So M transforms in the conjugate representation. So let us call that representation 15 bar. And again, the field small m doesn't transform under anything. So this is simple. Now we need to figure out what U1H is. Okay, so we can assign various charges to these two fields. And then once we do that, the charges of capital M and small m will be fixed from the superpotential. Okay? And also the assignment of charges to Q and Q tilde has to be free of anomalies. Okay? So the choice which turns out to be anomaly free is half, minus 3/2, minus 1, and 3. Okay? Check that it is not anomalous. What do you need to do to check that these assignments are not anomalous? Which anomaly you need to compute? Okay. Trace U1H, this SU2 gauge squared. Okay. Compute that anomaly for this symmetry with these representations and see that you get that this symmetry is non-anomalous. And then the R symmetry assignment that I will choose are 5 9s 1/3, 8/9, and 4/3. Okay, something weird. Now, claim. Okay, so these assignments are just assignments which are anomaly free and that you can assign. At this level, you don't know whether this R symmetry is the superconformal R symmetry or not. It might be not superconformal R symmetry. Why it might be not superconformal R symmetry? Because you have this U1H, okay, which can mix with it. Claim, do a maximization, okay, try to admix this U1 symmetry to this U1 R symmetry, and you find that actually the admixture is 0, that this is what maximizes the A maximization. Okay, this is the superconformal R symmetry. I could start with some different mixing of these two, and these two symmetries would mix. Okay, so there is a computation to perform here to find the superconformal R symmetry. Okay. So again, this is a claim, but this is a claim you can easily verify that we found the superconformal R symmetry. What we will do next, we will compute the supersymmetric index of this theory. How we would compute the supersymmetric index? In the same way as we wrote down the index of SU2 with an F equals 3. It will be some integral, an SU2 integral, and we have contributions of all the fields which appear here. Okay? So again, I really encourage you to perform that computation. And I will only write the final result of the index. So the final result of the index looks like that. So we compute the index of this theory. And what we find is the following. I write the expansion of the index in these parameters Q and P. So to zeroth order in Q and P, I find the 1. What is the 1? What is the meaning of 1? This is the vacuum. Exactly like we had in the massive case, the meaning is the vacuum. When I continue, then I continue computing the index, and I find that there is a term which goes like 4/9, and then there is something which is weighed by h minus 1, where h is the parameter corresponding to this U1H, and then we have characters of SU2 times SU6 global symmetry. Okay? And the characters are like that. We have a 6, 2. We have something which it looks like in a 6-dimensional representation of SU6 and 2-dimensional representation of SU2 global symmetries. This SU2 and this SU6. We have also something which behaves like h to minus 1, and which is in 15 bar representation of the SU6 and the singlet of SU2. Okay? What are these things? Remember that we count operators. What do you think these terms correspond to? Which operators in this theory that we can build? Okay, so this is the easier part. What are these operators? These are just the m's. Okay? So these are just the m's. What are these guys? What is a gauge invariant operator that you can build? A simplest one. Just Q tilde. Okay, just go from one end of this quiver to another. Multiply these two fundamental guys, and you will get Q tilde. It transforms under this SU2 and transforms under this SU6. So this guy is just Q tilde. And if you compute the U1H charges, you will find that both of them have the same U1H charges, and these are the U1R symmetries that you have. Remember that the R symmetry, the way to read R symmetry from the factors of QP, the power which appears here is actually R symmetry divided by 2. Okay, so just you can go back to what we defined before. Then there are several other terms with powers which are smaller than 1 of QP. But then remember what we are interested in is in the first power of QP, in QP to the power 1. Do you remember what powers of QP which are smaller to 1 represent? What type of operators? These are the relevant operators. Okay? So we find that there are some relevant operators. And the power of QP will tell us how many marginal operators are minus conserved currents. So you perform this computation and you find the following thing. There is something which will transform in minus 35 and is singlet under SU2. It comes with a minus sign. So it's a conserved current. Conserved current of what it is? Of SU6. Okay, 35 is the dimension of the joint representation of SU6. So find minus 35, and it is in singlet of SU2. Another thing that you find is 1, 3. What is that? That is the conserved current of the SU2. Okay? You find another minus 1. That minus 1 is the conserved current of U1H. Okay? So these things you expect from UV computation. You don't find anything with positive signs. So you don't find any marginal operators. But then, surprise, surprise, you find that there is something else, which is minus 22. Okay? You find an additional term, which is in a 20-dimensional representation of SU6, and is a doublet of SU2. Okay? You can trace in the index where each one of these contributions comes from. For example, this guy will come from Q, from this field Q, and the fermion that comes from the Q, let me denote it by that, psi bar Q. This will come from the Q tilde psi Q tilde bar, okay? There are these different operators which contribute, and so on. And this will come from some complicated operator, okay? It will not come from a simple operator, from some operator which is basically a quartic in the fields. It's actually, to be more precise, there is an operator which contributes with a plus sign, which is in some representation, and in the minus sign, one of them is quartic in the fields, one of them is cubic in the fields, and in the end, only this term remains. So now we look at it, and there are, of course, many other terms. Now we look at it and we say, okay, Chris Beam and Abhijit Gadet told us that if you compute the index with the superconformal R symmetry, we performed a maximization, and we found that this is the superconformal R symmetry under the assumption that there are no accidental abelian symmetries. If we do that, we compute the index and we look at order QP, we should see marginal operators minus conserved currents. We identify some pieces as conserved currents we expect, but then there is an additional piece. Okay? So it has to be, if this assumption of no accidental symmetry is correct, that this whole thing is an adjoint representation of some group. Okay? Is this an adjoint representation of some group by itself? Okay? Do you know something with 40? Okay? I don't know of anything. Okay? So what actually happens here is, let us count just the number of currents that we have. So 35 plus 3 is 38. 20 times 2 is 40. So the number of conserved currents we have is 78. 78 is dimension of E6. Okay? If you know your exceptional group theory, the adjoint of E6 has a 78, is 78 dimensional. Now, moreover, the E6 has SU2 times SU6 maximal subgroup. You can decompose the adjoint of E6 into representations of SU2 times SU6. If you do that, what you will get is exactly that. You will get 35 of SU6, you will get 3 of SU2, and you will get this guy. So it's not just the number which fits E6, it's just that the decomposition into the symmetries that you see in the UV fits E6. So that's it. We have proven that this theory has E6 global symmetry in the infrared. Okay, with very stupid tools that I managed to squeeze into one blackboard in the beginning. Okay, this is something that if you tell somebody that this simple gauge theory has an E6 symmetry in the infrared, how do you know that? It sounds crazy, where it will come from. Okay, and the argument for that is very, very simple. Okay, so now several comments. We looked at it and we find that there is 78 here. We're happy, we get an emergent symmetry which is E6. But we made some assumption. The assumption that there are no emergent U1 symmetries. So now we need to do more work. At least we need to see that everything else that we can do fits with this E6 symmetry. If we have an E6 symmetry in the infrared, we should see not just conserved currents at order QP, we need to see that everything, all the operators that we see in the index form E6 representations. Okay? Here I wrote something which appears at order QP to the power 4 over 9. Okay? So we have this U1 symmetry, which comes for the ride. So we have an operator which is in 6 times 2 representation, plus 15 bar times 1 representation. So what is the size of this representation? Or what is the number of these operators which have this R charge and this U1 charge? It's 12 coming from here, plus 15 coming from here is 27. What is 27? 27 is the fundamental representation of E6. And if you study your group theory and you see how you decompose the fundamental of E6 into the SU6 times SU2 subgroup, that's exactly what you will get. An SU6, like a 6-2 and a 15 bar 1, okay? So again, this is consistent with the 6. In principle, what you could have found here minus 78, but you would look at other terms in the expansion of the index and you would not find E6 representation. What would that mean? One thing it would mean is that you made a mistake, but say you didn't make a mistake, what would that mean? Exactly, that your assumptions are wrong. You perform the computation, one of your assumptions is wrong. There are 2 assumptions that you made. One is that there are no emergent U1 symmetries. So that might mean that there is an emergent U1 symmetry that you missed. Another more basic assumption that you made is that you go to a conformal field theory, that you flow to a CFT. Okay, this is something I assume all along, but we should remember that there is that assumption. So this computation that you get marginals minus currents, it is under the assumption that you have the full conformal symmetry in the infrared. Okay? So one of these things has to be not true, but here you can perform a variety of checks and everything is consistent with that you have 78. Now, to simplify my life, I added this field here, this M which coupled to Q tilde, Q tilde. I didn't have to do that. I could just flow with this field. What I would find then, if I would do that, I would find that the field Q tilde squared has R charge 2/3. What does it mean that the field, if a chiral operator, Q tilde squared, has R charge 2/3? What that means, just from what we discussed before, it's a free field, okay? So if we wouldn't have added this interaction, we would have a free field. We would have an interacting CFT with a free field. A free field would come with its own U1 symmetry. There will be an accidental U1 symmetry which would rotate this field. So if I wouldn't added this field, we would have gotten an emergent U1 symmetry. But that is an emergent symmetry that we understand. We can really see that there is a free field, and that free field will be rotated by some U1 symmetry, and it basically doesn't affect our logic, okay? When I add this interaction, what I actually do, again, the proper way of thinking is to do everything in steps, every time turning on one deformation. So first you gauge, then you add this M, you flow, you actually will see in the index that you get a free field. Okay, you see that you get free field. Then what I basically understand that this Q tilde is a free field. I introduce another free field with this coupling. So at the fixed point, at this fixed point, what is this interaction? I have a free field times a free field. Okay? This guy becomes a free field. So what is this term? It's a mass term. So basically what I did, I just gave that free field a mass and I integrated it out. Okay? And that's what made my life easier. But it's like a hindsight, logic, like the way to discover these things and doing it step by step and then discovering them. Okay, so this is our first example of a non-trivial emergence of symmetry. Okay, there are other examples that we can discuss, but here it happens in a really interesting and funny way. And one goal that I will have in the following lectures is actually to try to explain to you geometrically where this C6 comes from. From here, it's complete accident. Like it's a simple theory. We just study it. You know, I could split this 8 not into 6 and 2. I could do it. I could do other crazy things. But if I do this thing, which is completely unmotivated, I get an E6 global symmetry. Okay, so remember, we ask these questions of why. There are these dualities, there are these emergence of symmetries that happen, and an interesting question is why, and we will try to answer that question why with some more sophisticated geometric arguments. Okay, is this clear? Okay. There are many more things to be said about this, this emergence of symmetry. In particular, it is related in a tricky way to Seiberg duality, but in lieu of time, I will skip the discussion. We will not need it for the following. And I will just start in the several minutes that I have left. I have 8 minutes, or, right? Okay. I will start another developing another type of a tool, which will be very important for us. Okay, it actually won't be another tool. It will be an algorithm to do something based, again, on the same tools that we had on the first blackboard in the beginning of this lecture. The question I will want to answer is as follows. Say somebody gives me a CFT, hands to me a CFT. Okay? By hands to me a CFT, I mean I don't need a Lagrangian. I'm very modest person. I don't need everything to know about this theory. But I want something. So for example, I want that somebody will give me, say, the conformal anomalies, the A and C anomalies. Will give me the other anomalies, like the 't Hooft anomalies, and in particular, say, the global symmetry, that denote the global symmetry of this theory by GF. And I also want the other interesting things with which I can play with. For example, various types of indices. I don't need all of them, but at least some of this information. And I will now ask the following question. This is some strongly coupled CFT, maybe, some theory. It might have a Lagrangian, might not have a Lagrangian, I don't know, but it is some CFT. And I want to ask the following question. Is there a chance that this CFT, abstractly defined CFT that I was given, sits on is connected by a continuous deformation to a Lagrangian? So the picture I want to ask is like that. I have this CFT, and maybe it has exactly marginal deformations. If I tune them, I will arrive at some point, you know, maybe at strong coupling, where a Lagrangian description exists. Okay. This space of exactly marginal deformations that we discussed is typically called the conformal manifold of the theory. Okay. A conformal manifold is nothing more and nothing less than just a space of all exactly marginal deformations of a theory. Okay. And we have discussed how to compute the dimension of this space, of this manifold. Okay. So this is the question. There is an abstractly defined theory, and I want to look for a Lagrangian description of the theory. Okay? That Lagrangian description might be far away in the space of couplings. Saying it otherwise, starting from this Lagrangian, we will assume that this Lagrangian is conformal in the sense that, you know, it's Lagrangian which has exactly marginal deformation, that we can start from this free theory and continuously tune some coupling without generating any flow. And then we tune that coupling maybe to strong coupling starting here, and we will obtain the CFT that we started with, this abstractly defined CFT. Okay? Again, this seems a question to be a question which is completely non-tractable. In particular, I want to allow going to strong coupling. Okay? So I am given some CFT, and I want to ask whether, you know, even if are these strong coupling walls, whether I can find a Lagrangian description of that CFT. The point is that I can easily do it with what we have discussed on the first blackboard of this lecture. So let me start performing this discussion. So to start the discussion, I only need these two anomalies, A and C anomalies. Okay? Now, remember that there is a relation between A and C anomalies and 't Hooft anomalies of R symmetry. Okay? Now, what I want to assume is that the same A and C anomalies can be obtained in a Lagrangian theory. Why do I say that? Say there is a Lagrangian theory with free fields, and I start changing exactly marginal couplings, like the couplings of the theory, and go somewhere to different CFTs. What happens to A and C? Do they change or they don't change? They don't change. Why they don't change? Because they are related to these 't Hooft anomalies, okay, which are invariants under these types of continuous deformations. Okay? So the A and C anomalies of my theory should be the same as A and C anomalies of this Lagrangian theory. Okay? But if I have a Lagrangian theory, which is given in terms of free fields, I can compute the A and C anomalies using these free fields. Okay? So I can write the following equation. The A anomaly has to be equal to the number of free fields that I have in this Lagrangian, let me denote it by n chi, times the contribution to the anomaly of the free fields, I denote by a chi. And we computed it in the previous lecture. If I'm not mistaken, it's 1/48. I should remember that, but I never remember. But you have it. And for today, we don't need it. Later, we will need it. I will write it again. Okay, and then it's a Lagrangian theory, so it has chiral fields, but it also can have vector fields. So, and there will be a contribution to the anomaly coming from vector fields. And this C anomaly will be, again, given by the contribution of this n chi chiral fields, which is now another number C chi, plus the same NV, which is here, times the contribution to the C anomaly of the vector fields. So what does this equation give me? A and C are given to me by some person, or some abstractly defined CFT. These numbers are just some numbers which are contributions of free fields. They are fixed. Okay? Why they are fixed? Because free fields have very particular R symmetries. Free chiral fields have R symmetry which is 2/3. Okay? And the gauginos have R symmetry which is 1. And then I have here two numbers which define for me CFT, and two numbers which specify a Lagrangian. They don't completely specify the Lagrangian, but they tell me something about the Lagrangian. They tell me that from this simple linear equation, I can deduce the number of chiral fields and the number of vector fields that this Lagrangian should have. Okay? Now you give me some crazy anomalies A and C. I compute from them, solving this equation for n chi and nv. Say I get n chi and nv which are equal to some fractional numbers. What does it mean? That it cannot be that the theory I was given has a Lagrangian description somewhere on its conformal manifold. It just cannot be. If it would be the case, these numbers had to be integers. They're just number of chiral fields and number of vector fields. So if that is not true, if the numbers are fractional, that's it. I just have proven something which is non-trivial, that nowhere you will go on the conformal manifold, you will be able to write a fully Lagrangian description, a conformal Lagrangian description of your theory. And again, by conformal Lagrangian, I mean a theory which doesn't flow. It still might be that there is another Lagrangian that you deform that flows to this theory. Okay? The only thing we're discussing here is the Lagrangian which doesn't flow, which you just turn on exactly marginal deformations. Okay? If these numbers are integer, I can work harder. So what I need to do now, I need to now find a gauge theory with this number of vector fields and this number of matter fields, which will be first conformal, okay, that all the beta functions will vanish, okay, that's what we are looking for. And the list of such theories will be finite. It might be still empty, okay, but it will be finite. Given a number of vector fields, there is just a finite number of conformal theories you can write with this number of matter fields. So first of all, you write all the conformal field theories that you can with NV vectors and N chiral fields. Then what you do, you go to the other information that the kind person provided to you. Okay? For example, you look at these explicit Lagrangians that you obtained and ask yourself, is the global symmetry of that theory the same as the global symmetry that you want to get? At least when you deform the theory with exactly marginal deformations. Are the 't Hooft anomalies of these symmetries the same as you want? Okay? If an answer to one of these questions is no, okay, then tough luck. The Lagrangian has the same A and C anomalies. It's a conformal Lagrangian, but it cannot describe the CFT you are looking for. If the kind person is extremely kind and provided for you the index, you compute the index of this theory with the Lagrangian. The index is also invariant under continuous deformations. It is type of a Witten index. It has to agree with the index computed here. If everything agrees, you have a putative Lagrangian description. You still haven't proven anything, but you found a conjecture for a Lagrangian description of your CFT. Okay? And this will be an extremely powerful technique to find Lagrangians, conformal Lagrangians to many cases, some cases that we will discuss in the next lecture. And again, it is a conjecture in the same sense that Seiberg duality is conjecture. You are checking all of this special counting information that you can check, the same type of information. But it is algorithmic. Given a CFT, you can always ask yourself whether there is a Lagrangian which describes that CFT. Okay, so next time what we will do, we will start from a simple example of application of this algorithm. And then we will start discussing geometry. And we will apply this algorithm also in geometric setup.